By now you have quite the experience with exponents. So you've seen positive exponents, negative exponents. We've seen fractional exponents, and now we will explore just any real number as an exponent. But first, let's begin with the warm-up. So using what we know about exponents, let's evaluate 16 to the 1/2. Well, we remember that a raised to a fractional exponent, m over n, is nothing more than a radical, and the index of that radical is the denominator of our exponent. So the denominator of this exponent is n, so our index of our radical is n, and we have the nth root of a to the m. So 16 to the 1/2 will be a square root of 16. Now, what's the index? It's 2. And with a radical, we do not write a 2 for an index. It's understood. So the square root of 16 is 4. What about part B, 125 to the negative 2/3? Well, a negative exponent means that we will put that on the other side of the fraction. So we will have 125 in the denominator, and that 125 will be raised to the 2/3 power. Now again, we know that the cube root will represent the denominator of that exponent, so 3 becomes the index, and then 125. And now we could also, back here for this rule, the nth root of a to the m, we can write this as the nth root of a, and then raise that to the m power. Either way is acceptable. And so since 125 has a nice cube root, let's go ahead and take that cube root before we raise it to the second power. So the cube root of 125 is 5. And then we have to still square that. So we end up with 1 over 25. So what if the exponent were a real number but not rational? So for example, if we have 5 raised to the square root of 3. Square root of 3 is not a fraction, so I can't use the properties that we know up to this point. So what we do is we'll look at the square root of 3 as an approximation. So 1.7 is close to the square root of 3, and I can take and write 1.7 as 17 over 10. So I can take the 10th root of 5 to the 17th, and we get this. So this is a number that we understand. The problem is this 17/10 isn't the square root of 3. So let's approximate the square root of 3 even better. So 1.73. That can be rewritten as 173 over 100, and then 5 raised to that power would be the 100th root of 5 to the 173. And we get this. But we can approximate the square root of 3 even better, and so on. And so what we can do is we can approximate 5 to the square root of 3 by continuing to do this process. And you'll notice that our numbers start to land on 16.2424, and then we have some more decimal places trailing. So just to be clear, this is not the exact value. This is an approximation. If we were to talk about the exact, this is exact. Now, we can use our calculator to approximate these. So if we want to find 4 to the pi, on our calculator, we're going to find the caret key, which it looks like a little up arrow. So 4 caret, and then we'll use the pi button. And so 4 to the pi is approximately, go ahead and punch it in your calculator and see what you obtain. We're supposed to round to 3 decimal places, so we have 77 0.8802, so on and so forth, but we only need 3 decimal places, so let's look at our rounding rules, and so 0 would remain, and so our answer is 77.880. You'll notice that I'm using the approximation symbol, not the equals. Now, our calculators will also do order of operations. So we can go 6.7 in part B, and then we can open up a parenthesis, and then we can write 2, divide by 3, or you can use a fraction key there, if you know how to use fractions. And then that caret, and then we will want to use the square root button, 2, and then don't forget to close the parenthesis on that. And so from that, we should obtain 3.7761, and then our rounding rules say that if we want to round to 3 decimal places, the 1 makes the 6 stay. And so there's our answer. So the laws of exponents that we've learned up to this point from algebra will apply to any exponent that's a real number. So any exponent that you face should work the same as you've always experienced. So as long as our bases are the same and we're multiplying, we can add the exponents. If our bases are the same and we're dividing, we can subtract the exponents. A to the 0 equals 1, and that's true if A does not equal 0. And A to the S, then raised to the T, we can multiply the exponents. Then A, B, all raised to the S, we can apply that exponent to A and to B individually, so A to the S, B to the S. A negative exponent will go ahead and move that to the opposite side of the fraction. And notice the sign doesn't change. And then 1 to a power is just 1.